Welcome back, everyone, and happy Friday. I hope everybody's had a pretty good week here. I know that also this week there has been some information from RIT talking about the reopening plan and how things are going to go in the fall. I don't want to spend time talking about that today in class, but if you do have questions, I'm not sure I'm privy to any information beyond what's available publicly. But if you do have questions or you'd like to sort of just meet and talk, I think that office hours on Monday, both the 10 o'clock office hour and the 3 o'clock office hour, might be good venues for kind of town hall type questions if you have any. And that'll give us some time to kind of sit and discuss if you have any questions or concerns. But while we're waiting for that, we're working our way through thermodynamics. Last class, we were introduced to Brayton cycles, which are the power cycles that we use in natural gas-fired power plants. And today, we're going to talk about how we can improve thermal efficiency in these same Brayton cycles. So just as a review, the Brayton cycle looks like a Rankine cycle. The difference is, so it's still a heat engine. It's still got a series of open system components. The difference is that the fluid is different. So now we're talking about an ideal gas or an air as our working fluid. And so the way we're going to fix the states is going to be a little bit different for each one of these components. But because it's still a heat engine, we still talk about thermal efficiency. So we're going to define the efficiency of these engines as the net power divided by the heat in. And the net power is the power that's developed by the turbine plus the power that's consumed by the compressor. We're going to add those things up here. If we're drawing PV or TS diagrams, they look like this. Remember, when the working fluid is air, it's really important to look for these isentropic processes, or at least the processes that could be isentropic if the process was ideal. So here is the compressor, and here is the turbine. And those are the two processes where we can use those special isentropic relationships that we know for ideal gases. Remember, those relationships are different whether we're talking about variable specific heat or constant specific heat. The other thing we can see from drawing these diagrams is that when we're adding heat or when we're rejecting heat, this happens at constant pressure. So that means that in this case, the pressure when we enter our combustor and when we exit our combustor are the same. And we're also assuming here that the pressure of the exhaust gas is equal to the pressure of the gas that we're taking in from the environment here at state 1. For all of these components, because they're open processes, we'll use the open system version of the first law. We'll make assumptions like all these processes are at steady state. They all have one inlet and one outlet, or at least many of them do. We'll always neglect changes in kinetic and potential energy. And then for different processes, we will often decide whether or not they're adiabatic or passive. In this lecture, we'll also talk about a new component that's both adiabatic and passive. And then we'll assume that there's no friction losses, right? That's why we can say that it's constant pressure heat addition and heat rejection. We'll also say that there's no heat loss in the lines between our different components. When we do that, we'll get expressions here that we're used to seeing, where if we're trying to find power, we'll get m dot times H in minus H out, positive for the turbine, negative for the compressor. Here I have the subscript still as P, or pump, because a compressor is like a pump. It's just increasing the pressure of a gas instead of a liquid. For heat rejection, we'll get m dot times H out minus H in. And we know that when we're adding heat, like we do in the combustor, that's going to be a positive value. And when we're rejecting heat, or at least when we're modeling a process as rejecting heat, then we'll have a negative value for the heat transfer rate. Then we get to this question of how are we supposed to find H or delta H? So to answer that, first we have to know what the fluid is. In this case, it's an ideal gas. But remember, what's the fluid is always a two-part question. For ideal gases, first, we've identified that it's an ideal gas, but then we have to figure out if it's constant specific heat or variable specific heat, right? So variable specific heat would be an air standard analysis. Constant specific heat would be a cold air standard analysis. So for an air standard analysis with variable specific heat, we'll actually find the individual values of H, which means that we'll find delta H by knowing H1, and in this case, H2S. If we're looking at an isentropic process, which is sort of assumed here between 1 and 2S, so this, if we're using sort of the standard nomenclature for the state numbers, this is an isentropic process through the compressor. Here, we're going to say that the compressor pressure ratio is equal to the ratio of the reduced pressures that we would find on table A22. So here, in this case, we would probably be able to fix state 1 because maybe they tell us a temperature here. We can go on table A22 and look up PR1. We'll know this ratio of pressures, and that will let us find PR2. And once we find PR2, we can interpolate backwards and find everything we need to know about that second state. We get all that information from A22 if it's metric or A22E if it's imperial or English units. If it's a cold air standard analysis, we'll use constant specific heat, and that means we'll never find the individual enthalpies in the problem. Instead, we'll model delta H as the specific heat at constant pressure, or CP, times delta T. Then we'll have to find the temperature. In this case, this is the temperature at the end of an isentropic process. To do that, we need to look for some expression with K in the exponent. Remember, we can only use this if it's an ideal gas and if it's an isentropic process. And here, unlike with the internal combustion engines, we know the pressure ratios, not the volume ratios. So I look for the expression that has the ratio of temperatures and the ratio of pressures with K up in the exponent. So when I do that, I can find T2S. And that's what we did last class in the example. And we found, at least for that example, we found the net work, but we also found an isentropic efficiency just under 45%. So now, just like when we looked at the Rankine cycle, it's reasonable to ask, how can we improve thermal efficiency? And that's the question we're going to try to answer in today's lecture. So we're still talking about Brayton cycles, but now we're going to try to, again, think about how we move from the basic Brayton cycle into something that looks like a more complicated and a more efficient version of the Brayton cycle. We like to increase thermal efficiency because it improves economic outcomes and it improves environmental outcomes. So this is kind of a win-win situation. Just like when we talked about the Rankine cycle, there's some different strategies that we can employ, and many of the strategies are similar to the ones we talked about in the Rankine cycle. So we talked about regeneration in the Rankine cycle. If you remember, what we did with regeneration in the Rankine cycle was we split off some of our hot mass between a high pressure and a low pressure turbine, and we used that to preheat the fluid before it went into the steam generator. So we can do something similar, although it's a little easier to analyze in Brayton cycles because we won't split the mass. But here we can use exhaust gas to preheat our intake air before it goes into the combustor. We can use reheat, right? Just like we did in the Rankine cycle, between that high pressure and low pressure turbine, we can heat the mass back up and go through the low pressure turbine with more enthalpy at the inlet. But then we'll talk about something that we don't talk about with Rankine cycles, and that's intercooling. So intercooling is kind of the cooling side analogy to reheat. So in reheat, we split that turbine into two turbines, a high pressure and a low pressure turbine, and we heated the fluid up in between, right? And that meant we got more work out. Intercooling happens when we're putting work in, when we're compressing the fluid. And we talked last time about how backwork ratios were higher in these Brayton cycles when we're using air, right? So it takes more work to increase the pressure of a gas than a liquid because it's compressible. So here what we do is we go through a low pressure compressor and then we cool the fluid down and then we go through a high pressure compressor. So intercooling is kind of like reheat. It's just on the opposite side when we're compressing the fluid. So regeneration is what we'll talk about first. So in regeneration, what we're trying to do is capture some of this heat that we would otherwise waste, right? So here we know that 4, this is really an exhaust port out into the environment. But that air at that point still has some temperature. So what we try to do with regeneration is capture some of that enthalpy that's still in that exhaust fluid and transfer it into the fluid that's coming into the combustor here. So what we do is our system now looks something like this. So we have air that comes into our compressor, and then after it comes out of our compressor at this higher pressure, it goes into this regenerator. The regenerator is this heat exchanger. So the cold side comes through here, but then we have our hot exhaust gas coming out of 4 that's on the other side of this heat exchanger. So now we're cooling down this exhaust gas while we're heating up the gas that's going into our combustor. So this is nice because we want our exhaust temperature to be lower because that has less environmental impact if we're thinking about, flora and fauna that are sort of near our power plant, right? This is good for them to lower that temperature. But it also means that we're preheating the fluid that's going into the combustor, so that means we're putting less heat in to get the same amount of work out of the turbine, right? So this is good. We're kind of winning on both sides here. This is just, a bit of an animation, right? So we get this blue dot that's coming through the compressor. That's the cold fluid. The hot dot is red. That's coming out of the turbine. And so we're cooling down the hot exhaust gas while we're heating up the gas that's going into the combustor. So what does this look like if we draw it on a TS diagram, right? So here, regeneration, it's the maximum temperature that we could ever regenerate up to is the temperature coming out at 4. That's our exhaust gas. That's like the temperature in your oven, right? So if you put in, I may or may not have done this when I was an undergraduate. If you put a frozen pizza into an oven at, say, 350 degrees and you forget about it, then eventually that pizza will get up to 350 degrees and will probably be a charred mess inside the oven. Now, the temperature can't get any higher than 350 degrees because that's the temperature of the oven, right? So here our regenerator can only heat up this fluid before it goes into the combustor up to the temperature that it was at state 4. So without regeneration, we're adding heat in the combustor all the way from state 2 to state 3. But what happens with the regenerator, so we know that this is Q dot over M dot is H out minus H in, right? Or H3 minus H2. With regeneration, what happens here is we've added some heat to state 2 through the regenerator. So we've come part of the way up this curve, right? The maximum we could get to up here is this dashed line because that's the same temperature at state 4, right? That's the temperature of our oven. We can't get any hotter than that. And usually we won't even get quite up to that temperature. Just like you take, if you're doing it right, you take that frozen pizza out of the oven before it gets to the temperature of the oven, right? So here with regeneration, we'll only be adding heat to heat up our fluid from X to 3, right? So here, this is going to be less heat that we're adding. So we're not changing the net work, but we're reducing the amount of heat that we add. And when we do that, we're increasing our thermal efficiency because we're reducing the denominator, right? Because it's net work divided by heat in. So how do we sort of define our regenerator efficiency, right? This is thermodynamics, so we have a different efficiency for everything, right? But all these efficiencies mean something, right? So what we do is now we're going to look at our regenerator, right? And we can do a first law analysis on the regenerator and find out how much heat leaves our hot side and how much heat goes into our cold side. So when we're talking about thermal efficiency or we're talking about regenerator efficiency for this regenerator, we know that the maximum temperature that we can get to in the regenerator is the temperature at 4. There's no way that we can get hotter than that, right? So we know that's the maximum amount of heat that we can put in, right? Is if we heated up this input air into the combustor up to the temperature that it would be at state 4. Right now, if we were thinking about temperatures in a cold air standard analysis, we'd think about it this way. But if we're thinking about a variable specific heat analysis, another way of saying this is that the enthalpy at X, where we come out of the regenerator here, has to be less than the enthalpy at 4, going into the hot side of the regenerator. That's the maximum that we can get, and we probably can't actually get to that maximum, at least without a lot of cost, right? So we're going to define this efficiency of the regenerator as actual heat transferred in our regenerator divided by the maximum heat transferred in our regenerator. So the actual heat that gets transferred is going to be the heat, right? So this is the heat that's transferred to the air before it enters the combustor. So we're going from state 2 to state X. So if we can make all the assumptions that we'd usually make, this would be, if we were trying to find Q dot actual, this would be M dot times HX minus H2, right? Or we could talk about little q dot and just divide out the M dot because they're going to be the same in the actual case and in the maximum case. So in our numerator, we're going to have HX minus H2, which is proportional to the heat transfer rate that we get into the cold side here from the regenerator. Now, the maximum amount of heat that we can transfer into the cold side would be if we went all the way up to this maximum temperature T4. And at T4, the enthalpy would be the same as H4. So the maximum heat we could add in the regenerator to the cold fluid would be H4 minus H2. So now if we look at this regenerator efficiency, this is going to be HX minus H2 divided by H4 minus H2. Right? Which is really just the actual amount of heat that we're putting into this air before it gets to the combustor, divided by the maximum amount of heat that we could put into that same air. Regenerator efficiencies typically run between 60 and 80%. You probably could get better than that if you increase the cost associated with making this heat exchanger. Basically, you'd have to make it very, very long. And even then, it's really hard to get to a point where there's such low resistance between the hot side and the cold side here that you'd come out at the same temperature here. You'll learn a little bit about heat exchanger design when you get to heat transfer, right? Which is maybe a year or two down the road for most of you. So that's how we deal with regeneration, right? But another strategy we can employ here is reheat. Now, reheat we talked about with Rankine cycles, and this is basically the same thing, where we're splitting our one turbine into two turbines. So now we have a low pressure turbine and a high pressure, or a high pressure turbine and a low pressure turbine. And in between them, we add some more heat, right? This is kind of like, if one turbine is good, maybe two turbines are better. And if we have an ideal cycle, then what happens here is, we have this vertical line down. We stop at some intermediate pressure instead of coming all the way down to 4 prime. Which was sort of the simple Brayton cycle we looked at last time. So now we come all the way down here, but then we add some more heat, so we come up to state B, and then we go through another isentropic turbine, and then we cool the fluid down back to state 1. So what we've done here is we added this little bleb on the side here, right? And we know for these isentropic or ideal cycles that the area inside this TS diagram is the net heat, and the net heat would be equal to the net work. So what happens here is we added this little extra area here, which I've circled and colored in this sort of transparent blue. So that means that we've added more work. And what happens is we increase the work in a way that that increases the thermal efficiency, right? So the net work is going up in a way that the efficiency gets higher. So what's cool here is that if you're using reheat and regeneration together, you get some added benefits, right? Because here, if we're not using reheat, then our exhaust temperature is down here at 4 prime. But if we're using reheat, we have this higher exhaust temperature here at state 4. Now, normally you might think, well, a higher exhaust temperature, that sounds bad, right? Because we're going to be dumping more heat out into the environment. But in this case, we're using that higher exhaust temperature to feed into our regenerator and preheat the fluid before it gets into the combustor. So now, if we were not using reheat, then the most that we can add in our regenerator is up to this line here, which is T4 prime. But with reheat, we can go all the way up here. If we could get 100% efficiency, we could go all the way up here to T4, right? And then we'd have to put less heat in as we move in between here, right? So when you combine reheat and regeneration, what happens is you end up putting even less heat in because you get to regenerate better, right? So regeneration without reheat, maybe you could go from, state 2 up to this dash line at 4 prime, and then you'd have to add heat to go from here all the way up to state 3. But if you add reheat, then what happens is your regenerator could go all the way up here to T4, and you'd add less heat from T4 to, up here to state 3. Right? Now you got to also remember that you have to add some extra heat in here, but you're also getting more work out of the system. So, in business speak, they talk about this as synergy, right? So you get sort of two different components, or two different strategies, but when you put them together, you actually get more benefit than if you did each of the strategies separately, right? So there's some synergistic effects here because when you put these two things together, it actually works better than if you did each of these two things separately, right? Or what you might expect from just adding the two benefits together. So the other strategy here that's new to us, right? So this is not something we did with Rankine cycles, is we'll do this thing called intercooling. Intercooling is kind of like reheat, but it happens during the compression. So, compression is kind of the opposite of expansion, which we get through the turbines. So in between the turbines, we add heat. So in between the compression, we're actually going to cool the fluid down. So now, instead of just having one compressor, we're going to have two compressors. And in between these two compressors, we're going to transfer some heat out of our gas so that it's easier to compress as it goes through this second stage compressor, right? So it takes a little bit less work to get up to the pressure that we want. Now, we never did this in Rankine cycles because it didn't take that much work to increase the pressure of that liquid. But remember, we talked about how the backwork ratios in these natural gas power plants are typically much higher than what you'd see in a Rankine cycle. So now we're going to use this strategy as well to improve our net work by reducing the power required to compress the gas up to the temperature that we want. Right? So this is sort of the natural gas, or the Brayton cycle with reheat, right? I couldn't find a picture from the textbook where they add intercooling. So here I just kind of drew it on myself. So you'll have to excuse me for sort of the crude picture here. But now, if we use the states here, so between our first compressor is 1 to state C, and then we intercool between C and D, and then we compress up to state 2. So what we would do here on our TS diagram is we have a vertical isentropic compression. If the compressor is ideal, we move up from state 1 to state 2. Then we cool the fluid down. Then we move up from state D to state 2 prime, and then we add heat all the way up to 3. So, you can think about this as, cooling it down is almost, I hate to say that it's like compression because the pressure doesn't actually increase, right? So this happens at constant pressure. But if you think about what happens to the molecules when you cool down air, is that the molecules do come a little bit closer together, right? Or at least they're vibrating less, so then it's easier to squish them together using that second compressor, right? So when we do this, you'll notice again that the area inside our curve gets bigger. That means our net work gets bigger. And here the network gets bigger, not because we're getting more power out of the turbines, but because we're putting less power in at the compressors. We also remember here that as we move between state C and D, we're rejecting some heat. So the work increases here because the area inside our cycle increases. So intercooling reduces the compressor power, which increases the net work, but then we also have to reject a little bit of extra heat here too. So those are kind of the three strategies that we use in Brayton cycles to improve efficiency. Now, for the rest of the class, I'd like to go through an example where we use all of these strategies. So this is kind of like a Brayton cycle with all the trimmings. So here, right, what happens is we're pulling in air from the environment, right? It has a temperature and a pressure and a mass flow rate. We go through the first compressor. We're told the compression ratios in a bit of a weird way that the total compression ratio is 10 and that the compression ratio is equal between the first compressor and the second compressor. So after we get out of the first compressor, then we cool the fluid down. We go through this second compressor. Now we get up to the pressure we want to be at, but the fluid's still kind of cool. So we're going to go up into the regenerator. So that's going to use the exhaust gas to preheat our fluid before it gets into the combustor. This first stage of combustor is going to increase the temperature of our gas at this high pressure. Then we're going to come out of the combustor, go through the first turbine, let the gas expand, the pressure goes down, right? And we get some power out. Then we're going to reheat, we're going to increase this temperature at the intermediate pressure and go through the second turbine. Now we've got this relatively high temperature exhaust gas, but we're going to have it come through here and we're going to cool that exhaust gas down while we're sort of taking advantage by heating up this air before it goes into the combustor. So that's kind of what's going on here. And this question, I think it's from the textbook, tells us or asks us to draw a TS diagram for the cycle, to determine the thermal efficiency of the system, to determine the backwork ratio of the system, and to just kind of track the assumptions that we make as we move through the problem. So I'm not going to get a numerical answer for this problem, but I'm going to show you how to fix. So first I'm going to show you how to get all the symbolic equations, which I think is really important, right? This is, if we're following that kind of 80-20 principle, you can demonstrate that you know what you're doing by getting those symbolic solutions. Then I'm going to show you, without finding the numbers, I'm going to show you how to fix all the states in this problem. And there's a lot of states in this problem. I'm going to show you how to do it with a variable specific heat analysis and with a constant specific heat analysis. But because we don't have an infinite amount of time, I'm not actually going to go through the math to get final answers, right? So if this was an exam, right, this would be a little bit intimidating, right? Because you would look at this state table and you'd say like, oh man, there's a lot of states here. If I just go by the number, it looks like 10, but I have 2 state 9s, I have 2 state 7s, I have 2 state 4s, and I have 2 state 2s, because in all of these cases, there's like the ideal exit and the real exit from turbines and compressors. So really, I think I have 14 states here, and I know like one state where I have the temperature and the pressure, and then I know temperatures at like 3 other states. So it feels like I don't know a lot of information here, but this is enough information to solve the whole problem. If this was an exam, you probably wouldn't have this many blank spaces on the state table. We'd probably sort of fill this in partially and then specifically ask you certain processes so you could demonstrate that you knew how to fix certain states, right? But if I had to do this whole thing, how would I go through this problem, right? First, it asked me to draw a TS diagram. So I know that the lowest temperature in my problem is 300 degrees, right? And that happens at the inlet, right? So that's going to be state 1. I also know that I'm pulling this air in from the atmosphere, and it told me that the pressure here was 100 kilopascals. So I have these 2 lines, and where these 2 lines intersect, that's my first state. I'm also told that state 3 happens at this same temperature. So we're going to go through from state 1 to state 2, we go through some kind of compressor, and then we cool the fluid back down to this same low temperature, 300 degrees. That happens at some intermediate pressure, right? So here I have P2, which is equal to P3, which is equal to P7, which is equal to P8, right? So now between states 1 and 2, what I have to do is I go through this ideal compression, right, or isentropic compression, and then some intercooling to reduce the temperature back down to state 3. So now I know that my maximum pressure is 10 times higher than my minimum pressure. So I have a high pressure line. Remember, as the pressures are going up on a TS diagram, right, these lines are getting higher. So P6 is going to be the maximum pressure here. It's also going to be the same as P4 and 5, right? And it's going to be 10 times what P1 is. So it's 1,000 kilopascals. So I know that the maximum temperature in my system here is 1400. Now to get from state 3 to state 6, first I go through an isentropic compression to get up to state 4S. Now I'm going to heat the fluid all the way up to state 6. Now you'll notice we're going from 4 to 6 because somewhere in between here is going to be the exit of the regenerator. Because the first way that we add heat to this fluid at state 4 is by transferring some heat from the exhaust gas. But I don't know exactly where to put that state point yet, so I'm just going to leave it blank. But I know that there's going to be some state 5 somewhere in between state 4 and state 6 here. But I know that state 5 can't be higher than the exhaust temperature, and I haven't plotted that on my graph yet, so I don't know exactly where to put it. But after we get to state 6, I know that I'm going to come out of an isentropic turbine, right? So then I'm going to go down through a turbine here, so I'm going to reduce my pressure, let that gas expand and get some work out to state 7S. Then, because there's some reheat, I'm going to stay at this same pressure, add some more heat. The problem says till the temperature gets back up to 1400 degrees Kelvin. Then I'm going to go through this low pressure turbine to get to state 9S, right? That's the isentropic outlet of the second turbine. Now, I guess theoretically, even though it's not quite true because there's an open system here, this gets exhausted eventually, we're going to go down to state 1. But remember, there's state 10 that's in here that's the outlet of the hot side of the regenerator. So here, now I know that state 5, right? So I'm going to use this exhaust gas at state 9 to heat up the fluid, to preheat the fluid from state 4 to state 5, right? So I know state 5 has to have a temperature that's less than state 9. And then I know that as I move from state 9 to state 10 through the hot side of the regenerator, I'm staying at constant pressure, but my temperature is going down. So this is not too bad. We're almost done here, but we haven't put in, we've only had ideal compressors and turbines so far. So we need to add the real states. And in all of the real states, the specific entropy has to be bigger than the specific entropy from the ideal states, right? So in this first real compressor, we're having the same pressure difference, but we're increasing the entropy through the real turbine or through the real compressor. Same thing through the second compressor. Through the first real turbine, again, now we're decreasing the pressure, but we go between these two pressure lines, but S at 7 has to be bigger than S at 7S. Same thing with state 9. So now, this is a pretty tough TS diagram to draw because there's so many states on it. But now we're finished, right? We systematically went through, we drew our high pressure, our low pressure, and our intermediate pressure. And then we know that as we're cooling, we're moving left on these constant pressure lines. As we're heating, we're moving right on these constant pressure lines. And I know that the temperature at 5 has to be less than the temperature at 9. So I'm pretty happy with this TS diagram. Might not be perfect, but I've kind of demonstrated that I understand how to draw TS diagrams for these processes. Now, I got to find, I think, the thermal efficiency and the backwork ratio. In order to do that, I need to do a first law analysis on all these open components inside the system. So here, right, we'll make assumptions that look like this. So steady state, most of these are one inlet, one outlet, but not the regenerator. There's no kinetic or potential energy change. We're going to say that they're adiabatic for turbines and compressors, that they're passive for heat exchangers, at least for the combustors and the intercoolers. There's no frictional losses and no heat losses. So our thermal efficiency is going to look like this. Our desired energy effect is going to be the net power, and the energy cost is going to be the heat in, right? Because we got to burn this natural gas, right? Because the mass flow rates everywhere are the same. This is not like a Rankine cycle with regeneration where we're splitting the mass. There's only one mass flow rate in this problem. So we can do little w.net divided by little q.net and not be too worried about what happens. Right? And we know that little w.net is the sum of all the turbine and compressor powers. We'll let the first law worry about the signs. Q.in is going to be the sum of all the places where we're adding heat. So we can write it like the textbook would write, which I have it up here, or you can leave this as you would get it out of the first law. Either way, you're going to get an expression like this that's all specific enthalpies. If we were doing a cold air standard analysis, or we said constant specific heat, we would take all these delta H's on the top and the bottom, and we would factor out Cp, and we'd get a function that's all just delta T's. The thing about a constant specific heat analysis is that the specific heat is not just constant for one process, it's constant for all of the processes, which means that there's only one specific heat in the problem, which means I can cancel out these Cp's and my thermal efficiency in a constant specific heat problem is only going to be a function of temperatures. Otherwise, my specific heat or my thermal efficiency is going to be a function of only specific enthalpies. Backwork ratio is going to be the sum of all the pump, or in this case, compressor powers, divided by the sum of all the turbine powers. So we get something that looks like this if we wanted to use absolute values like the textbook does. Right? So we can turn that into an expression that's only about specific enthalpies, or again, we can pull out the specific heats and get this only as a function of temperatures. So now that I've done this, we've gone through what are all the assumptions that I made for each component to get to this point, and I have symbolic solutions for the thermal efficiency and the backwork ratio. So the only thing we've got left to do is fix the states, right? Which makes it sound like it's trivial. It's obviously not. Fixing all the states is a lot of work, and if you're doing the homework and you got 14 states to fix, it's probably going to take you a lot of time. But we won't get numerical answers here, but I am going to go through and show you the methodology for how you would fix all of these states if you were doing variable or constant specific heat analysis. So the first thing that we notice about our state table is I actually don't need all of the states in the symbolic solutions that I have, right? So there's no 2s or 4s or 7s or 9s inside my final expressions. But because I know the compressor efficiencies and the turbine efficiencies, then I have to find first the isentropic outlets, and then I use the isentropic outlets and the efficiencies, the isentropic efficiencies, to find the real outlets. So even though something like H2S is not in my final expression, I'm still going to need to find it, because if I don't, I won't be able to find H2. So what do? The first thing that I look for when I'm doing an ideal gas problem like this is temperatures. So any place that I know the temperature, that means I can automatically go and look it up on table A22 and find H. The other thing that I didn't write down on my state table here, because this is an ideal gas problem, and because it's open systems, it's a series of open systems where I know the pressure ratios, here, instead of the specific volume, which I don't think I'm ever going to need in this problem, instead, I would write down probably PR here and find the reduced pressures at all the states. But here, everywhere where I know the temperatures, I can go through and get H, and I could get PR. So that means I already can fix all of state 1. I can fix state 3 except for the pressure. I can fix state 6 except for the pressure, and I can fix state 8 except for the pressure. And really, when I drew the TS diagrams, I've already shown that I know what these pressures are, because the problem gave me, in kind of a roundabout way, the compressor pressure ratios. So here, I can look up these states, find the enthalpies, and find the reduced pressures. If I'm dealing with a cycle that has an ideal gas as the working fluid, remember, I got to have, like the Obi-Wan voice in the back of my head that's, Professor Schertzer telling me, look for the isentropic processes, right? So the isentropic processes are always going to be the key for these ideal gas problems, right? Because the isentropic relationships are going to let us move between 1 and 2s. They're going to let us move between 3 and 4s, 6 and 7s, 8 and 9s, right? Because I have these special isentropic relationships. So let's first go between state 1 and state 2s. So there's two ways to do this, right? Am I using variable specific heat or air standard analysis, or am I using constant specific heat or cold air standard analysis? If it's air standard, I'm actually going to find the enthalpies by looking stuff up on table A22. Here, between state 1 and state 2, I know this is an isentropic process. Because it's an isentropic process, I know that the ratio of the pressures is going to be equal to the ratio of the reduced pressures. I know PR1 because I knew T1, and I can pull this off the table if I interpolate. So when I do this, right, I know this ratio. The only thing I don't know here is PR2. So for state 2s, when I find PR2, I can interpolate kind of backwards and find H2s, and I can find T of 2s as well. I would get that from table A22, or if this was an imperial problem, A22E. In a cold air standard analysis, I'm never going to find the individual enthalpies. Instead, what I'm going to look for is, or what I'm going to model delta H as, is Cp times delta T. Now, I know Cp, or at least I could look it up in a textbook. I know T1, but I don't know T2s. Right? So how do I get T2s? Again, I got to use the isentropic relationship. But here, I'm using the isentropic relationship for constant specific heat, which I know has to have K in the exponent. So I look for equations with K in the exponent, and I look for something that relates the ratio of temperatures to the ratio of pressures. Now here, I know this pressure ratio, I know K, and I know T1, so the only thing I don't know is T2s. So once I get that, I can put it into my table, and I will have fixed the isentropic outlet from the first compressor. So now how do I get to the real outlet for that first compressor? And the answer is I got to look at the isentropic efficiency. So the isentropic efficiency, remember, it's always power over power, but we got to think, are we putting power in or getting power out? For compressors and pumps, we take the ideal power divided by the real power, right? From a first law analysis with the assumptions I make, I know that I can get this expression as a function of enthalpies, or I can then use the constant specific heat assumption to get this as a function of temperatures, right? In variable specific heat, the only thing I don't know in this expression is H2. For constant specific heat, the only thing I don't know in this expression is T2. So with the isentropic efficiency and the exit from the ideal or isentropic compressor, I can find the exit from the real compressor. So now I fixed state 2. State 3 I already fixed because they gave me the temperature, right? And as we move from state 2 to state 3, what happens is we have this intercooling that happens at constant pressure, so P3 is equal to P2. Now I go between 3 and 4s. This is again an isentropic compressor. So we go through the same process that we did to find 2s, right? So in air standard analysis, we're going to use the ratio of pressures is equal to the ratio of reduced pressures. I'm going to get these from table A22, right? I'll get when I had, because I knew T3, so I can get PR3. I know this ratio of pressures because it's given in a roundabout way in the problem. So the only thing I don't know is PR4. From here, I'll get PR4, and I'll use that to interpolate to find H4s and T4s. In the constant specific heat analysis, again, delta H becomes Cp times delta T. The only thing here I don't know is T4s, so I got to use this isentropic relationship for constant specific heat, which puts K in the exponent, and I have something about temperature ratios and pressure ratios. So now I found state 4s. So the next thing that I have to do is try to find state 4, right? And this is just like trying to find the real outlet of the first compressor. Now I know the isentropic outlet, and I know the isentropic efficiency for this second compressor. So here, I know that, again, I can use this isentropic efficiency, right? If I know the ideal power, which I do because I know state 3 and state 4s, I don't know the real power because I don't know H4, but the good news is I know the compressor efficiency, so the only thing here I don't know is H4, so I can isolate this to find H4, or if I use constant specific heat, I pull specific heat out of the numerator and the denominator, and I can use the temperature at T4s and the isentropic efficiency to find the temperature at state 4. So if I can do the first compressor, I can do the second compressor too. So if this was an exam, I probably wouldn't get you to do both the compressors because I only need you to show me that you know how to do it one time, right? There's no need to duplicate that work, right? You don't have to demonstrate the same thing twice. So now how do we do state 5? Right? State 5, we're going through the regenerator. So here we know the regenerator efficiency is Q actual divided by Q max. Q actual is going to be H5 minus H4. Q max is going to be H9 minus H4. It's helpful that we already drew the TS diagram so you can see what Q max would be. Here we don't know, so we do know the regenerator efficiency, but we don't know H5 and we don't know H9. So I'm going to leave this one here for a bit, right? So this is true also for temperatures. We don't know T5 and we don't know T9. So I have a symbolic equation that will let me find H5 if I knew H9, right? Or it would let me find H9 if I knew H5, right? So I'm going to leave this for a little while because I got one equation with two unknowns, which means that I can't solve this yet, but I've got a symbolic solution, so at least I've demonstrated that I know how to do this, right? So when you do this, if you get stuck, look for the next state where you know the temperature, because then you can kind of go through all this process again, right? So here we know the temperature going into the first turbine, right? That's state 6. So this is kind of like the compressors, but now we're going through turbines, right? So again, we're going to first look through the isentropic turbine, right? We use this isentropic relationship. There's an isentropic relationship for a variable specific heat analysis where we would find PR7. And there's an isentropic expression for constant specific heat analysis where we would find T7S, right? So that'll let us fix T7S. Now, to go through the real turbine, now we need the isentropic efficiency of the turbine, which was given in the problem. So here, we would use the turbine equation for isentropic efficiency, which is the real power divided by the ideal power. Because remember, the ideal power, or the ideal turbine, puts out more power than the real turbine. So here, again, the only thing we don't know is the enthalpy at the real exit. So we can go through and we can find H7 because we know H7S and we know the isentropic efficiency of the turbine. Or if we were using a cold air standard analysis, we would be finding T7 because we know T7S and eta for the turbine. We would do the same thing going through the second turbine. First, we would find the ideal exit of the turbine in either air standard or cold air standard analysis, right? So again, the trick is identifying which of these processes are isentropic, because when we know which processes are isentropic, we can get either this ratio of reduced pressures is equal to the ratio of pressures, or this expression with K in the exponent, right? So here we're going to find T9S, and then we're going to use the isentropic efficiency to find the real exit of the turbine in the same way that we did that through the first turbine, and actually in a way that's very similar that we did for both of the compressors. It's just that the turbine efficiency, the fraction gets inverted here. So that gives us state 9. Right? And now, because we know state 9, remember we left state 5 and we couldn't find state 5 because we didn't know state 9? But now we do know state 9. So we can revisit this equation we had for regenerator efficiency. Before, we didn't have H5 or H9. But now we know H9. The only thing we don't know now is H5 or T5 if we're doing constant specific heat. So now that I know state 9, I can go back to my symbolic solution and fix state 5. So now the only state we haven't fixed is state 10. So state 10, again, we're going to have to do the first law on the regenerator. So before, we did the first law on only the cold side of the regenerator to get the regenerator efficiency. But now we're going to do the first law across the whole regenerator, right? Remember, this is going to be a component that has more than one inlet and more than one outlet. So we'll say that it's at steady state, that there's no kinetic energy change and no potential energy change, that it's both adiabatic and passive, so we get rid of Q dot and W dot, no friction losses on either side, and no heat losses on either side, so all the heat that comes out of the hot side goes into the cold side. When we do that, we're going to get the sum of M dot in H in minus the sum of M dot out H out is equal to 0. So we look at our two inlet states. The cold inlet happens at state 4, the hot inlet at state 9. The cold outlet is state 5, and the hot outlet is state 10. So now, right, I can sort of collect by my terms on the hot side and the cold side. I recognize that the mass flow rates are the same, so they're going to drop out. And now the only thing that I don't know, because I fixed all these other states, the only thing I don't know here is H10. I fixed state 9. That let me fix state 5. And I fixed H4 going through that second real compressor. So here, now I get an expression for state 10 that's a function of H4, H5, and H9. If this was a constant specific heat analysis, before I isolated for H10, I would have pulled out the CP on both of these sides cancel it out just like I canceled out the mass flow rate, and I would get the expression that T10 is equal to T4 minus T5 plus T9. So if I do that, now I can fix state 10. And I've kind of gone through all of these states. Now I know this is a lot, right? This was 14 states. So it's nice to be able to do a problem like this, or to feel confident that you can do a problem like this, because if you can, that means you can fix all of the potential states in this problem. Now, if this was an exam problem, it's unlikely that you would have to fill in all 14 states. But you should still know how to do any of them, because if I gave you a problem like this, I would fill in part of the state table and let you demonstrate your understanding by filling in the rest of the state table. So that's all that I had to talk to you about today. Did you have any questions before we break for the weekend? All right. Thanks very much, everybody. I will see you on Monday. And again, if you'd like to sort of voice questions or concerns about the reopening, I will see you in office hours on